it needs to follow Huckel's rule.
Each carbon needs to be sp2.
Yeah, each carbon needs to be sp2. Yeah.
Yeah. And the third one,
Huckel's rule.
Huckel's rule. Okay, so what is Huckel's
Yeah.
rule?
I think it's the number of pi electrons, right? So the pi
Yeah.
electrons need to be either 2, 6, 10, or 14.
Yes, yes, yes. Okay, so let's see this one. So firstly, you tell me, is this compound is cyclic or not? First one, the first one.
Just give me a few minutes.
Yeah,
Okay,
sure.
so this is sp2, right?
Yeah.
sp2.
Okay, so I'll help you that each atom in this ring is sp2 hybridized. This nitrogen
Okay.
also. Yeah.
Okay.
Mm.
So that's one of the rules, and it's also cyclic. This
Cyclic. Yeah.
cyclic. Okay, cyclic means it's in a ring structure, right?
Yes, yes.
Okay, and then Huckel's rule. Let's see. There's
Okay, so I'll give you one more thing that the nitrogen in this case having a lone pair. Okay. So do you know
okay.
what is lone pair? Extra electrons, na?
Mm-hmm.
Okay. So in this case, the lone pairs are also used as pi electron.
Mm-hmm.
Do you remember resonance? A little bit about resonance, how resonating
Yeah,
structure
yeah. Mm-hmm.
is. Okay. So how they will used in aromaticity? See, these lone pairs are coming here, and now these double bond will be delocalized. Okay. So how it will
Mm-hmm.
work? Okay. Now,
Mm-hmm.
from this structure, you identify that the given is aromatic or not. From the last, like this one.
Hmm. So it's sp2, so then it would also be cyclic, right? And
Yeah.
then
How many pi
um,
electrons are here?
it would be 3 pi bonds, so 6 pi.
Yes, it's 6 pi electrons. So is it follow Huckel's rule?
Yeah.
Yes, absolutely. So this is aromatic. Okay, so that's how we identify aromatic. And there is one more
Okay.
thing
Oh
in
my God.
Huckel's rule, yeah, that you can write that it follow 4n plus 2
4n+2.
pi electron. Here, n can be 1, 2, 3, 4. Okay, anything. You note
Okay.
down this thing also. Okay.
Yeah.
Okay. So after that, I'll give you some more example. Is that okay? Or you want to do in homework?
No, you can give me more examples. No, that's not an issue.
Because aromaticity will comes in your exam. It is very important.
I don't think we did number 3 though, ma'am.
So, number three, this one.
We didn't do that one, I think.
Okay. Can you erase this?
Yeah.
Okay, good. Okay, let's see the third one. Firstly, you tell me about third one that is the compound is cyclic or not? Is a closed ring type structure? The first one.
Yeah.
Yes, the first rule is followed. Second rule is all carbon is sp2 hybridized.
No.
How?
Wait. Oh no, sorry. Yeah.
Yes, all carbons are sp2 hybridized. Okay. Then the third. How many pi electrons are here?
And 4 times. So that's 8? What?
No. How we identify
Wait.
pi electrons? We don't need that formula. See,
Oh.
whenever there is any compound given, so we don't need any particular formula. If in case they will ask you what is the formula, then you need to tell that the formula will be 4n plus 2 pi electron. Okay. Why? We only need that if n is equals to 1. So in case of n is equals to 1, what will be the answer? How many pi electron will be there if the n is equals to 1? Tell me.
6.
Yes, 6 pi electron. And if 2, then it will be 10 pi electron.
Yeah.
Okay, that's so on. So now,
Yeah.
and if n is equals to 2, then in that case, if n is equals to 0, in that case,
Mm-hmm.
how many pi electrons?
2.
Sorry, yes, 2 pi electrons. Okay, so I told you now that we only need to remember that if any compound having 2 pi electrons, 6, 10, 14 pi electron, that then in that case they will follow Huckel's rule. Okay, so see, all these this whole compound have how many pi bond? First, you tell me how many pi bonds are there?
1, 2, right?
Yes, two pi bonds. And each
Mm-hmm.
pi bond have how many electrons?
2.
Two. So 2 pi means total how many electrons? 4 pi
4.
electrons. Yes.
Mm-hmm.
Okay. So now from the formula, is there any possibility that aromatic compound having 4 pi electrons?
No.
No. So
Mm-hmm.
this is not aromatic compound. Done.
Okay.
Not aromatic. Then after that, the aromaticity also classified further. Okay, that is also important. Wait a second.
Why is Huckel's rule important in determining aromaticity?
Because it is used to identify directly. See, there is three types of aromaticity. The first is aromatic, general aromatic. Okay. Then the second will be non-aromatic. So to differentiate aromatic and non-aromatic compounds, we need Huckel's rule. And the third one is alicyclic. Okay. So aromaticity will be identified by the three rules. Tell me all the rules. The first one is
It must be cyclic.
cyclic. Second one is sp2
Has every
hybridized.
sp2 carbon, yeah.
Yes. And the third is
Huckel's
4n
rule.
plus 2 pi electron. And in case of non-aromatic, all the rules are same as aromatic compound. The first one is cyclic.
Mm-hmm.
Second one needed be sp2 hybridized. And the third one is 4n pi electrons. So what is the difference in between these three rules?
I think the main thing is just like the pi electrons.
Yes.
Yeah.
Yeah. Okay. So where is the blue? Okay. So if I'm taking n is equals to 0 here, how many pi electrons? 2 pi electrons. If I'm
2.
taking
Yeah.
n is equals to 1, then how many pi electrons? 6.
Mm-hmm.
And n is equals to 2 in that case, 10 pi electrons.
Mm-hmm.
If in this case I'll take n is equals to 0, then how many pi electrons?
0, right?
0. So this is not possible, 0 pi electrons. After that, n is equals to 1. In that case, how many pi electrons?
Or sorry, what? Oh, 4 pi.
Yes, 4 pi.
Oh,
And then
yeah.
in case of n is equals to 2, how many? 8
8.
pi electrons. And remaining all the aromatic and non-aromatic compound, the remains organic compounds, which is cyclic in nature and not homocyclic, they will lie in alicyclic, okay, in the alicyclic
Mm-hmm.
part. Now you understand that the given compound which I gave you, this one.
Mm-hmm.
So this is aromatic, non-aromatic, or alicyclic? Tell me.
Non-aromatic.
Yes, absolutely. How many pi electrons are here?
4.
Okay, good. And let's suppose I have one more example. Mm. Okay, now I'm giving you 10 compounds and you need to identify that. Okay, so firstly you take a screenshot of this one, or you want to take in the last.
I think the last maybe.
Okay, okay, so I'll give you some examples and you identify that the given compound is aromatic, anti-aromatic, or what type of compound. The first one. Is all carbon sp2 hybridized or not? Firstly identify that, okay?
Wait, sorry, can I annotate on here? Let me just annotate here. Oh my god, why does it keep doing that? Sp2, Sp2, uh, Sp2, 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 Sp2. I think all of them are Sp2. Yeah, Sp2, Sp2. Um, would this be? Hold on.
Which one? Yes, this is also sp2 hybridized. If
Yeah.
carbon is having positive charge, okay, so in that case it will be sp2 hybridized.
Oh, okay.
Hmm.
Wait. If carbon is positively charged, doesn't that mean it has a total of 6 electrons?
Yes.
Oh, oh wait, 2, 4, 6. Oh, I see. Okay. Wait, how can that be? Doesn't carbon need to have 4
Yes, it needs, but
bonds?
if in case it doesn't have, it needs to stabilize. But do you know carbocation?
Yeah, kind
Yes.
of, yeah.
Yeah. So in that case, it is positively charged. Okay, so there is total 6 examples. Okay.
Yeah.
Tell me each one.
I'm sorry, what do I say?
That the given is aromatic, anti-aromatic, non-aromatic.
Okay.
Wait a second. Here you write down non, not it will be anti-aromatic. Okay. Okay. Now you go through with each example, and now you tell me that the first one, firstly, that aromatic, anti-aromatic, or alicyclic. Sorry.
Actually, would it be a better idea if I wrote the notes down that you gave me?
Sure.
Or yeah, just so that I'm more prepared.
Yeah. Yes, yes.
Okay.
Okay.
Yeah.
Okay. So now you tell me for these six. Okay. After that, we start like a reaction mechanism. Is that okay? Can we start reaction
Yeah.
mechanism or you want stereochemistry? Tell me whatever topic you want.
Mm,
Which is your like favorite or you want to study?
what was stereochemistry again?
Okay, good. We'll start stereochemistry.
Sorry. I was asking what is that topic like?
Okay,
If I
okay.
can.
Okay, so in stereochemistry, do you know the enantiomer, diastereomers,
Oh
mirror,
yeah. Different types of molecules. Yeah.
yeah, plane or symmetries
Versions
and
of
all
the
of
same
them?
molecule. Yeah.
Yes, yes. So these are in stereochemistry.
Okay. Maybe we can talk about that then.
Okay,
Yeah.
so we'll start with stereochemistry.
Okay. Um, so do you want me
Okay.
to still do this? Okay.
Okay, so first one is aromatic or not.
Um,
Firstly, is the first thing is the compound is cyclic or not.
yeah.
Yes. So first thing, check. And the second thing is all carbon sp2 hybridized.
Yeah.
Yes. Then the third one. How many pi electrons are there? How many pi bonds? Firstly, you tell me. How many pi bonds in this case? In this whole
Five.
organ? Five. Five pi bonds multiplied by two means how many pi electrons? 10 pi electrons. So is Huckel rule needs 10 pi electrons?
Yeah.
Yes. So the third rule also check. So this given compound is aromatic. Okay. Now second one. Second one is the compound cyclic.
Um, yes.
Yes.
Or yeah.
Second, uh, that all carbon is sp2 hybridized.
Yeah.
Yeah. And how many pi electrons are there? How many pi bonds in this
One.
case?
One.
Ones. So how many pi electron? two
Just
pi
two.
electron. So
Mm-hmm.
is it follow
Yeah.
the Huckel rule?
Yeah.
Yeah. So the third one is also checked. So this given compound is aromatic. Done. Now the third one. Third one, cyclic or not?
Yeah.
First check. Second thing, hybridization.
Yeah.
Yes. And how many pi electrons?
Four. No, five. Sorry, that's four pi bonds times two is
Yeah,
eight electrons.
eight pi electron. So is it aromatic or anti-aromatic?
Anti.
Anti-aromatic. So it needs to be anti-aromatic, but it changes into non-aromatic. So this is important. You can note down that if in any case you are getting more or 8 pi electron, more than 8 pi electron or 8 pi electron in anti-aromatic, those compound will automatically change automatically change into non-aromatic. Why? Why they'll change into non-aromatic?
Oh, wait, sorry. Just give me one moment to write it down, ma'am. Sorry.
Yeah, yeah, sure.
Wait, sorry. I don't understand the difference between anti and non-aromatic. What's the difference?
Here's the difference, huh? The Huckel rule difference in Huckel rule. That aromatic shows 4n plus 2 pi electron, while anti-aromatic shows only 4n pi electron.
Yeah, no, no, I meant what's the difference between anti and non-aromatic? Because they seem very
And
similar.
okay, okay. So alicyclic is also known as non-aromatic.
Oh, okay. Yeah, I just wanted to make sure.
Yeah, okay, good.
They seem very similar, so.
Mhm. So you can note down one more thing in here, the stability order. Stability order. So aromatic is most stable aromatic, then non-aromatic, and in the end, anti-aromatic.
Okay.
Okay. So now you note down this thing also that if the pi electrons is 8 or more than 8, in that case, if the compound is anti-aromatic, those compound will automatically change into non-aromatic. Okay. So see the third
Mhm.
one. How many pi electrons third one?
Um, 16, or sorry, third molecule? Oh, sorry.
Third. 8 pi electrons, na? So 8 pi electrons lie in which
Oh,
aromatic or
yeah.
anti-aromatic?
Hmm?
8 pi electrons
Mm-hmm.
lies in which region? Like, is they belong in aromatic or anti-aromatic?
Anti.
Yes, anti. So, if any compound having more than 8 pi electrons or 8 pi electron, or they are following anti-aromatic rules, then they will automatically converting into non-aromatic. And why? What
Mm-hmm.
is the reason behind this? So, the reason is stability. Stability. Aromatic or non-aromatic, which is more stable?
Aromatic.
Hmm?
Aromatic?
Yeah. And in case of anti-aromatic and non-aromatic,
Um, Anti.
in non-aromatic and anti-aromatic.
Anti, yeah.
No.
Wait,
See, here
non-aromatic. Oh, okay.
there is stability order.
Yeah.
Non-aromatic is more stable than anti. So that's why anti-aromatic compounds change into non-aromatic to gain more stability.
Oh,
Okay. This is the reason.
yeah.
Okay. Okay, let's move to the fourth example. So fourth is similar as we discussed earlier. While in case of oxygen, we put nitrogen earlier.
Um, sorry.
Do you remember that case?
Huh?
Do you remember the case? This one.
Yeah,
This one.
yeah.
So this is aromatic, anti, or non-aromatic.
Mm, I think it's aromatic.
Yes. So this one, fourth one is also
Aromatic.
aromatic. Then sixth, oh sorry, fifth is all carbon. Firstly, is this compound is cyclic?
Yeah.
Yes. Then all carbon are sp2 hybridized.
No.
No. So the compound is
Non-aromatic.
sixth one. Cyclic.
Yeah.
Yes. sp2 hybridized all carbon.
Mm, no. Hold on. Give me one second. I don't think so.
Yeah. This one sp2 or not.
Yeah.
This one is also sp2. This carbocation sp2. All are sp2 except this
Yeah.
one. So this is sp2, sp or sp3 hybridized. Which
SP.
it is sp3.
SP3.
Yeah.
Oh, because of the hydrogen. Sorry, I'm forgetting the hydrogen.
Yes. Okay. So this is not
Mm-hmm.
having sp2 hybridization. So it also belongs in non-aromatic. Right. Okay, do you have any doubt in aromaticity? Firstly, you note down the. Do you want to note down or want to take screenshot?
Um, I just took a screenshot of it.
Okay. You can take screenshot up to now because this whole portion is
Yeah, can
related
you
to
start from
aromatic.
the beginning?
Do you take a screenshot for this one?
No. Is it okay if you can start from the beginning?
Yes, this is the starting part.
Oh, okay,
You can
sorry.
write
Yeah.
aromatic or you can write here aromaticity. Wait a second. Yeah, this is important. You need this portion. So you need to know some rules and via organic compound you directly can tell that the given is aromatic or not. So
Okay.
this one. From here, aromaticity portion will start. Okay. I'll share
Mhm.
a reference book also. So is if there is any examples are there, you'll go through with the example. And if you have any doubt, you can ask me in like next class. Okay. Related to aromaticity. I will share some questions also. Whenever you are free or available, you can solve them.
Mhm.
Okay.
Okay, you can keep going down and take a screenshot, no worries.
Okay.
Okay, I got that. Okay. Okay, I got everything. Thank you.
Okay. Now we'll start with stereochemistry.
Okay.
Okay. Okay. So, firstly, what is stereochemistry? Stereochemistry is majorly used to identify optical activity of any compound. Do you know what is optical activity?
Mm, no.
Okay. Chirality. Do you know any name related to this optical activity, chirality?
Yeah, chirality I remember, yeah.
Tell me.
Mm, I remember hearing about that word. I heard it I remember hearing about enantiomers, diastereomers. I remember hearing about that. Um, I think it has to do with like how you rotate the molecule or like
Yes, yes,
mirror
yes.
images or something like that. Yeah.
Yeah, yeah, very good.
Oh, I see. I kind of understand what optical, it's like how it appears to the human eye,
They
right?
change.
Yeah.
Yes, yes. The change, the direction of light.
Oh, okay, okay.
Yes. So that is belongs to optical activity. Okay. Optical activity and stereo of any particular compound. Wait a second, na? Okay. So firstly, we will start with our simplest portion, that is a Fisher isomerism. Okay, Fisher thing. So firstly, you tell me that let's suppose I have a organic compound, carbon. Okay, how many bond carbon have total?
4.
Four. If I'll represent the four carbon bonds like this, so the image of a carbon is in 2D mode. Yes or no? This is a
Yeah.
2D, yes, it is a 2D representation. Okay.
Mm-hmm. Mm-hmm.
Sorry. So to represent this 2D molecules into 3D, we come through with a solution, that is Fisher representation. Fisher representation. Do you know what about anything about Fisher
Is it like similar to like
represent?
Newman? Is it similar to like Newman projection?
Yes, Newman projections or hers. Absolutely. Right down the projections. So what is the difference in between Fisher and Newman?
I think Newman it accounts for like the strain in the molecule or between the different atoms, the space.
Like they are like majorly used to represent any 2D molecule into 3D, firstly. Okay.
Yeah.
Yes. And there is a certain rules in each Fisher, Newman, or Sohars. So what is Fisher representation? What is the majorly use of Fisher representation? So see, Fisher representation, firstly, as we know, it used to convert 2D molecules and into 3D molecules. And what is the major thing in Fisher? That is wedge dash
Oh.
representation. Okay.
Oh yeah, I remember this. Yeah, I remember.
Yeah,
Yeah.
so wedge dash representation. So how we
Mhm.
can write down the carbon with four bond? So see, in Fisher, we firstly need two bonds in the plane. Means we draw two bonds in a same plane as the carbon having. Okay. After that, we will represent a wedge form, wedge bond, and another will be dash bond. Okay.
Mhm.
So this is a wedge dash representation. Wedge dash representation. This bond is known as wedge bond, and this will be dash. Okay.
Mhm.
Wedge bond is used as let's suppose this is the plane molecule. This both the hydrogen and carbon is in same plane. Okay, and the hydrogen is both the first and second hydrogen is above the plane, and the second one is below the plane. Okay, so wedge form is
Mhm.
always represent above the form situation, above the plane, and this used as below the plane. Then what is above the plane? What is below the plane?
The hydrogen?
Yes, both above and below are hydrogens only.
Sorry, what was your question?
I'm just asking you, like, do you understand what is above the plane, what is the below the plane, the concepts?
Yeah, like spatially in 3D. Yeah, yeah. I'm
Yes, yes.
familiar with it. I've seen it before. Yeah.
Okay, okay. So I'll give you a question. Okay. And now you tell me that which is above the plane, which is below the plane. Mm,
Okay.
let's suppose I'm having this one. This is dashboard. Okay. So firstly, you tell me, is the representation is wedge dash representation?
Yeah.
Okay. And how many atoms in a plane in the question? How many atoms are lie in same plane? Maximum number of atoms.
Two?
Two or three?
Like,
Hmm? Two or
I
three.
think two.
And the carbon?
Or the carbon in the middle and then chlorine and hydrogen.
Yeah.
Right?
But carbon is also in the same plane as the two like these two. Sorry. As the two atoms are in, like chlorine and hydrogen and this carbon. All these
Mm-hmm.
three atoms lies in the same plane. Okay.
Yeah.
And how many above the plane and what is the group name which is in above the plane situation?
Um, ethane?
Yes, ethane is above the plane and below the plane.
Alkane? Okay.
Alkene.
Is it called alk? Wait, no, methane, all right?
Yeah, methane.
Sorry, I don't know why I said I was thinking of alkyl group. That's
Yeah.
something else.
Okay, okay. That is alkyl group.
Alkyl group, yeah.
Yeah. Okay, no issue. Okay. Sorry. Now, after wedge dash representation, okay. Do you understand wedge dash representation?
Mm-hmm.
Then there is three form which we can represent, and you also needs to know those forms. Okay. So the first one we will discuss about Fisher. Then we will discuss about Newman, and in the last we will discuss about Sohars. Okay. So first
Mm-hmm.
we will start with Fisher, and in stereochemistry you needs to understand the 3D geometry of any molecule. Okay, that is very important.
Mm-hmm.
Okay, so let's start with I'll change some molecules here in this above situation. Okay, I'll replace the hydrogens. Okay, I'll add fluorine, chlorine, bromine, and iodine. Okay,
Mm-hmm.
and fourth situation. Okay, now the major part will comes that how we will represent uh, each molecules which is in 3D form to 2D form. Okay. Okay. So firstly, in case of Fisher, we need to form a sign which totally represent like this one. Okay. And the middle portion here, this will represent the carbon. Okay. The middle dot will represent the carbon. And here is the fonts, four lines represent bonds. Okay.
Mm-hmm.
Do you have any doubt up to now? Anything?
Um, oh yeah, I think I want to say like I think I struggled a lot with this. Like I understand like how the wedge is above the plane and the dash is below the plane, but it was still a little hard for me to visualize like when all the reaction mechanisms were happening. I think it's in SN1, there's like a
Yes,
carbocation
yes,
intermediate. So like
yes.
the stereochemistry changes. So that's I think I had a little bit of trouble, not a little bit, like a lot of trouble there. And then I think like it was just hard for me to see like with the enantiomers and diastereomers like how it changes, if that makes sense. Like how does the yeah.
Yeah, yeah, I understand. So for that, you needs to understand the exact structure. I have one website. Wait a second, now I'll search for that. So, mm, wait a second. Mm. I'm not able to find out the exact website for now. There is a website which is like which is very useful to understand you that like how the molecules is looking like. Okay, so firstly, if you don't understand that how the molecules are arranged,
Mm-hmm.
you're not able to identify that from which side the nucleophile will attack, from which side the electrophile will attack. Okay, so you needed to identify the exact situation, the exact spatial rearrangement of each molecules, how they will
Mm-hmm.
look like in Fisher, Newman, and Sohor's projection. Okay. Okay, so
Mm-hmm.
I'll start with some basics like Fisher, Newman, and Sohars. Do you know anything about that? If you know, we'll skip that part.
I've had more experience with Newman. I don't think Fisher was that used in my course specifically. Not
Okay.
I'm not really sure about Sawhorse either. I'm more familiar with Newman, but I think Fisher could still be there. I'm not sure. With this new professor, I don't know. It's a like I'm at a different college, so I don't really know how they teach. Maybe they include Fisher, so maybe it could be helpful if I knew that how to do it.
Okay. Okay, I'll explain like something about Fisher, Newman, and Sohars, all the three one.
Hmm.
Okay. And
Yeah.
if you, yeah. So Fisher is, see, this one. Firstly, we will represent this sort of sign. Let's suppose first I will draw a line and the number of carbons. Let's suppose I have five carbons in any molecule. So I will add five lines, one, two, three, four, and five like that. Okay. So now these
Hmm.
dots represents carbon. Okay. And each four bonds are represent the bonds of carbon. Okay. Do you understand that? Each dot having four
Yeah.
lines.
Each star has four.
See, in this case, each dot, wait, this one, each dot. Let's suppose this is a dot. So how many lines? One, two, three, and four.
Oh yeah.
Okay, and let's suppose I'll have this one. So it also has four. One, two, three, and four.
Mm-hmm.
Okay, that's how. So each carbon atom having four lines. Done up to now?
Mm-hmm.
Okay. So that's how Fisher will represent. It represent like lines, and the lines are crossing over where the carbon lies. Okay. Now the next part in this will that these let's suppose this is a 3D, this one is a 3D representation, and I need to convert this 3D representation into Fisher form. Okay, like this one. So how I will go through with that? So let's suppose, firstly, I am putting my eye into here. Let's suppose this is my eye, and I'm putting my eye in between these wedge and dash form. Okay.
Mm-hmm.
And now, from this one, wedge and dash, I will see that here the I and bromine, iodine and bromine like this. Okay. And the chlorine and fluorine like this. Do you understand? If I'm
Mm-hmm.
standing here where my eyes are putting, so I will saw this into 3D, and iodine is in my left hand side because it is above the plane, and bromine is in right hand side because it is below the plane. So see,
Mm-hmm.
iodine is in left hand side, bromine is in right hand side. Okay. Then the chlorine is upside, so I'll put chlorine upside, and fluorine is downwards. Okay, so I will put fluorine like this. Do you understand this?
Mm-hmm.
Any doubt up to now? Okay, let's see. I have one more example. Let's suppose I will give you one more example. Uh, let's suppose here's mm, fluorine, fluorine, bromine, iodine. Okay, and here is the carbon. And now I'm uh, ask you to form a Fisher for this 3D representation. How you will draw? Firstly, you check how many carbons are there. So total, how many carbons in this case?
On.
One. So okay. So I will make a this one. Okay, one carbon. Okay. Then the next step will be that I'll put my eye on the direction from where wedge dash lies. Okay, like this. Okay, I'm standing here, this direction. Okay, from this direction, which is into left hand side. Think about it.
Um, like from the le oh, I see. On the left it's iodine, right?
Absolutely, very good. Iodine. And in right hand side,
Chlorine.
think about it. Think wisely, because fluorine and chlorine always lies in the same plane. Okay, so fluorine and chlorine will always in above the plane situation. Okay, and iodine and bromine only is in this direction. Do you understand?
Yeah. Yeah, so iodine is on the left and bromine's on the right. Oh,
Yeah.
okay. Yeah.
And fluorine, when the two molecules or atoms lies in the same plane, like this one, they are putting in the same line. Okay. Let's suppose I will give you one more example.
Oh, okay, okay, okay. I see. Yeah.
Okay. Let's suppose I will give you one more example. Okay, this is the compound, and now we need to represent this into fission. Okay, so what we are going to do, firstly, I will put a eye on here. Okay, we are going to put eye on the direction from where the wedge dash lie. Okay, after that, again, I will make a cross. Then, okay, so after this, in this case, let's suppose I'm standing here. So, which is in the right hand side?
Mm-hmm. CH3,
Absolutely, very good. And which is in left hand side?
C2H5.
Absolutely, very good. And then hydrogen is in above side and fluorine is in below side.
Mm-hmm.
Okay, so see, this representation is very useful in case of SN1 and SN2 and E1 and
Mm-hmm.
E2 chain. Okay, so in that case, what will happen? Let's suppose this is fluorine, or let's suppose I'll give you one
Mm-hmm.
more example. Okay, so OH will be there. This will be carbon, and like this. Okay, this is the organic compound. And now, in the case, let's suppose I'll remove the bromine one firstly. So I'll have CS3 here, let's suppose. Okay, and the reaction will be SN1 reaction. And in case of SN1 reaction, do you know anything about SN1?
Yeah, it's a not a concerted reaction. No, no, no. It's not a concerted reaction. It happens like SN1. I think it means like you have to have a stable. How do I remember if there's a stable carbocation or something like that?
Yeah, yeah.
The ha Yeah.
So
So
in this
everything
case,
happens in one step, right?
yes, in this case, carbocation will form.
Yeah.
Okay, so SN1 is used for formation of carbocation basically. Okay, so
Mm-hmm.
in SN1 case, carbocation will form. So what is carbocation? Carbocation is a basically three or six electron species. Okay, so in this
Mm-hmm.
case, how I will convert this compound into carbocation? I needs to remove one element from this case. So what I will
Mm-hmm.
do, that I'll remove the OH one, okay,
Mm-hmm.
and converting this into carbocation. In carbocation case, we needs one more thing, that carbocation is a planar structure. Okay, so after removal of OH, this compound is represent like this: hydrogen, Cl, and CH3. Okay, and carbocation. Carbocation means this vacant p orbital. Okay, do you have any doubt?
Vacant, sorry, can you say that again?
Yeah, sure. So see, SN1 and SN2. Okay, so I will like go with SN2 also. Okay, so you will understand the major difference in between SN1 and SN2 also. Okay, so it will SN2. So firstly SN1. In case of SN1, you know that a carbocation will form. Okay, so what is carbocation? Carbocation is basically a six electron species. Okay,
Mm-hmm.
and in carbocation there is a vacant p orbital.
Mm-hmm.
Vacant p orbital. So this is the vacant p orbital. This one. Okay,
Mm-hmm.
you will understand in the end that what is the need of this vacant p orbital. Okay, so this is carbocation and vacant p orbital. After that, the in case of SN2, in case of SN2, there is not any intermediate will form. This is a concerted mechanism. Okay. In this
Mm-hmm.
case, completely backside attack will occurs. Yes or no?
Oh yeah, I remember, yeah.
Yes. Okay. So
Yeah.
in this case, also we need to remove this OH. Okay, this OH will needs to
Mhm.
remove. So how the let's suppose I have a nucleophile. Okay, and now this nucleophile needs to
Mhm.
attack on this compound. So from which direction this nucleophile will attack? If I need to remove this OH.
Mhm. For SN2?
So, yes, in SN2.
Can you ask that again? What direction
From which direction this nucleophile will attack in this compound, in this
for
given compound?
SN2 it's
Yes,
backside, right?
backside, absolutely. And which organic, organic compound, like in this organic compound, which element is completely opposite direction from the OH?
Mm. Completely in opposite direction. I think it would be CH3, right?
Yes, it is a CH3. Okay, good. So which element will replaced in this case? CH3. So what you needs to do that if OH is in the wedge direction, so in case of SN2, after attacking of nucleophile, CS3 will come on the wedge direction. Okay. And as
Mm-hmm.
nucleophile is attacking on this direction, so nucleophile is completely comes to opposite and this compound will form. Okay, so I'll describe you one more time that how it will proceed. That let's suppose nucleophile. I'm having a nucleophile. I'll
Mm-hmm.
putting this nucleophile here. Let's suppose here is a nucleophile. Okay. Now this nucleophile attack on the carbon and it needs to removal of OH. Okay. This
Mm-hmm.
nucleophile attack towards completely backside.
Mm-hmm.
Okay. And completely backside when it attacks, then this OH will remove and a place towards OH will remain empty. Okay, and the CH3 will comes to the OH position and the nucleophile comes to the CH3 position because it attack toward backside na, it needs a backside position only. So that's why the nucleo wait a second, I need to attach a nucleophile here because nucleophile attack from backside na. So nucleophile will coming here and the CH3 will coming to the OH position. Okay, let's suppose I will give you one more example. Carbon, chlorine, chlorine, hydrogen, and CH3. Okay, I'm giving you a nucleophile. Let's suppose that nucleophile will be OH, OH negative. Okay,
Mm-hmm.
okay, and I'm giving you that this OH will attack on the carbon and it will remove chlorine and it will proceed through SN2 mechanism. Okay.
Mm-hmm.
Now this will attack to the carbon and the chlorine will remove. Yes or no?
Mm-hmm.
Why chlorine will remove firstly, not fluorine?
Fluorine is a lot more strong.
Do you know the living group tendency?
Oh, it triggers something in my memory. I just remember everything. Yeah,
Okay.
about that.
So living group tendency means which group leave firstly if we are talking about halides. So iodine is a more living group tendency than bromine, then chlorine, and then fluorine. So in between chlorine and fluorine, chlorine having more living group tendency to it.
Mm-hmm.
Okay,
Yeah.
remove easily. Okay, so
Mm-hmm.
let's suppose OH will attack on the carbon and chlorine will remove. It is a complete backside attack. Okay, so
Mm-hmm.
OH needs a backside position. Yes or no?
Mm-hmm.
And In this case, which atom is opposite to the chlorine?
Opposite to chlorine is fluorine, yeah.
It's fluorine. So it needs to vacant that position for OH. Okay. So what process will occur? That chlorine will remove and OH comes to the complete opposite direction of the chlorine, and the fluorine, which needs also a more vacancy or more position, so it come to the chlorine position. So it will be like this. The chlorine will come here and OH completely attacked through the backside, and then the fluorine comes to upside or below the plane. Okay. Can I give you one example so you'll understand more?
Um,
Yeah.
so yeah, so so the opposite OH replaces fluorine. Uh, oh, it's on the opposite side now, right? Because it used to be wedge, now it's dash fluorine. Whereas, oh, because it replaced it. Okay, I see. It replaced it and then chlorine left. So fluorine is in chlorine's place, then OH is in the fluorine's place. It's just like replacing the nuclide is just replacing the fluorine, right?
See, in this case, there is a whole mechanism.
Mm-hmm.
Like this is a chlorine. So, as this chlorine, it also having
Mm-hmm.
a backside vacant orbital also. Okay, so
Uh,
nucleophile will attack on the vacant orbital, then that chlorine will remove. Okay, and the vacant orbital is in the place of fluorine, then the fluorine will comes to here. That is the whole mechanism for that. Okay, but if you need, you can directly solve from that this one. That if let's suppose if I am having a living group on the wedge direction,
mm-hmm.
how you will directly tackle the questions. Okay, so let's suppose I am having a living group on wedge direction. Okay, this at this
Mm-hmm.
position. So what I'll do, I will attach any group which is on the dash direction to this place and the upcoming nucleophile on the opposite direction. Okay, you only needs to do that thing because in case of SN2 you needs a backside attack.
Mm-hmm.
Okay, while let's suppose if SN1 will come. In case of SN1, see, in case of SN1 there is not any backside attack or anything like that in case of SN1. So in SN1, the nucleophile will come and attack from both the direction. Okay, so the compound can be 50-50% like this one.
Oh,
Do you remember that?
yeah. Is that like the enantiomer ratio?
Yes,
Racemic mixture
yes,
or
yes.
something like that,
Racemic
right?
mixture. That is, yes, yes, that is
Yeah,
racemic
racemic
mixture.
mixture.
Okay, so in case of SN1, that's why we are having racemic mixture, while in case of SN2, we are getting inversion. So that inversion is known as, do you remember that name of that inversion? It's Walden inversion.
Chirality? Oh, no, never mind. Sorry. Chirality is something different. Oh.
Okay, it's Walden. Okay, so this is used in SN1 reaction or SN2 reaction, and that's why we need stereochemistry to understand whole the structures of the molecules. Okay, do you have any doubt,
Mm.
anything from the geometry portion? If you have, we can solve your doubt first. Okay, after that we will move further.
Can you hear me?
Yeah.
Oh, okay, sorry. I thought I like muted myself. No, I was saying, just to like reiterate, so for SN1, the nucleophile attacks from the backside, so it's basically adding to an empty orbital for CH3, right?
Mm-hmm.
Is
Yeah.
that or is it adding to the orbital of carbon or CH3?
Uh,
Mm.
like the nucleophile attack on which direction do you want to? Wait a second. Okay. Sorry. So a nucleophile attack on the back direction. Okay. And the majorly a pentagon structure will form in case of SN2. Okay. Let's suppose here is a nucleophile, and nucleophile when attack on the back side, it not directly attack to CS3 position. It attack to a back side of living group. Okay, so firstly we need to identify that which group is a living group. Okay,
Oh, okay, okay. Yeah.
that is the most important thing. And after a living group, what we are going to do, we add a group which is directly opposite to the living group. We will add to that one, and after that the vacant position we are going to add the nucleophile. So nucleophile
Yeah.
doesn't directly attack to the CH3 group or opposite one. Nucleophile firstly attack to vacant orbital. Vacant orbital of
Mhm.
which element? Vacant orbital of living group.
Hmm.
Okay. After the
Mhm.
vacant orbital attacking, they will shift their position.
So in this case, it's OH, right? Not CH3? Not CH3, OH. Okay.
In this case, the living group is OH.
Okay.
Okay. And if I am talking about SN1 case, so in that case, what will happen? In case
This
of
is SN1.
backside attack is related to SN2 here. While
Okay,
in
SN2.
yes, in case of SN1C,
Mhm.
in case of SN1, there is no any particular backside attack will be there.
Oh, okay.
Okay, so in case of SN1, the nucleophile can be attacked from backside or can be attacked from the front side. Why? Because it converting into carbocation.
Hmm.
Okay, so whenever it converting into carbocation, there is two possibilities. See, this is the vacant pure vital, na? So there is two possibility from nucleophile attacks. Okay, so after that, it depends. Let's suppose I am here having hydrogen here and here is
Mhm.
chlorine. Okay, so which group is larger in size? Hydrogen or chlorine?
Chlorine?
Chlorine, absolutely. Chlorine is larger in size. So chlorine also has some space. It also occupies some space, while hydrogen is lesser in size. So nucleophile attack from which direction? That think about this. Like nucleophile attack from which direction? If it has a more space as compared to this one. So nucleophile will prefer the site from the attacking or the group which attached to the carbon is smaller. Okay, so in compare to hydrogen and chlorine, nucleophile will attack from the hydrogen side because it occupy less space as compared
Mhm.
to chlorine. Okay, and it has more space for the nucleophile, upcoming nucleophile also. Okay, so it
Okay.
also depend that what sort of living group are there and what sort of attaching atoms or attaching groups to the carbon. Okay, so all
Mhm.
of this depends upon the whole organic compound. We will start with SN1 and SN2 in case of, I think it is an alcohol portion. So whenever we go through with functional group and their mechanism, na, so in that case, we will go through with the SN1 and SN2, E1 and E2.
Okay.
You are having alcohol in your syllabus, na?
I would have to double check. I think I sent one to Dhananjay sir,
Yes,
so
there.
I
Yes,
think that
yes, yes.
one.
Yeah. So alcohol, phenol, amides, heterocyclic aldehyde, ketones, all of them are in your syllabus. Okay. So whenever we are discussing each groups. So in that case, we will go through with in detail SN1 and SN2, because SN1 and SN2 needs a lot of like basis. So you need to identify firstly that which is living group, what is nucleophile, what is electrophile.
Hmm.
Do you know about
Yeah.
that?
Yeah, nucleophile, electrophile, and then there's some that are weak, some that are strong, right? Same with leaving group.
Yeah, yeah. So what
Yeah.
is nucleophile? Can you tell me?
Nucleophile means they like electrophile means they love it loves electrons, so
Yeah,
it wants
yeah.
more electrons. Yeah.
Then
But
nucleophile means
nucleophile,
positive charge. Yeah.
yeah.
Okay, okay, okay. Okay. So in stereo, in stereochemistry, you firstly needs to identify the 3D structure. Then after 3D, you need Fisher. Okay,
Mhm.
like that. And after that, in case SN1 and SN2, if you didn't understand SN1 and SN2 in detail, so whenever we discuss alcohol, we will go through one more time, and in that case, we will go through from the basis of SN1 and SN2. Okay.
Okay.
Yes. Okay.
Yeah.
So from next class, we are going to. mm
Wait, sorry, were we supposed to have a 3 hour class? Or sorry, because then the J sir told me we were supposed to have a